Welcome back. Now that we've had a look at how the peer review system is set up to work, the different types of evidence and study designs that scientists have available in their toolkits, as well as some of the basic statistical concepts that are useful in being a thoughtful skeptic, let's turn to the many things that can go wrong in science. To do so, we'll dive into a field of research called meta-science, or meta-research, which is the use of scientific methodology to study science itself. Most of this research focuses on the medical and psychological sciences and related fields, so my focus will be on these fields. As we explore some of these issues, it should be clear that the main problem underlying many of them is the existence of perverse incentives. That's the first topic I'm going to explore. At times, the peer review process can be slow and expensive. There can be inconsistency by those doing the reviewing. And there is evidence of bias, particularly against women, in the awarding of grants. A major incentive at the heart of peer review is what has been termed publish or perish. This refers to the pressure on scientists to produce publishable results. This has many effects that we'll discuss throughout the video. Another problem is the current system by which funding is granted for scientific research. With more and more scientists chasing a fixed amount of available funds for research, the acceptance rate for grants has gone down considerably. These perverse incentives have many effects on the quality of science that is published. These issues aren't all the result of these bad incentives, but many are. Let's start with a pervasive issue: publication bias. Publication bias occurs when certain studies are left unpublished. These are usually studies that have negative results, which are not as interesting to researchers or journals. This leaves a lopsided and thus distorted impression of what the available science says. In fact, a 25-year review of the biomedical literature found that 96% of the abstracts that reported p-values reported at least one p-value under the 0.05 level of statistical significance. This is also related to another issue that we'll discuss in a moment. The prevalence of publication bias varies depending on the field and how it is measured. In orthopedics, a meta-analysis revealed that between 12 and 19% of all papers go unpublished. In the psychological sciences, a review of meta-analyses indicated that 25% of them revealed issues with publication bias. Countless studies have revealed that pharmaceutical companies are much more likely to publish positive clinical trial results and less likely to publish negative results for drugs than are independently or government-funded studies. Dr. Ben Goldacre investigated this issue thoroughly in his book Bad Pharma. There are statistical tests to detect publication bias, such as the funnel plot, though none are bulletproof. In the last decade or so, various initiatives have been implemented to address this problem. After Goldacre's book was published, he set up the All Trials project with the goal of having all trials registered and all results reported. In the US, the NIH's clinicaltrials.gov registry was set up to mandate pre-registration of clinical trials, though enforcement is still lacking. However, there is good reason to think this has helped, as studies have documented a much greater likelihood to report negative trial results since year 2000. Furthermore, peer-reviewed journals have been established with the specific focus of publishing negative or null results. Optimistically, in more recent meta-analyses, publication bias has been found to be much less than in older studies. And despite the high prevalence of publication bias found overall in meta-analyses, in most cases they are not found to affect the conclusions, which means that scientific consensus is unlikely to be significantly affected by publication bias. Still, it's clear that further efforts are needed to curb the problem. The next issue I'll discuss is the various statistical blunders that are often made in scientific papers. Perhaps the most famous is what's called p-hacking, also known as data dredging or phishing. Remember discussing p-values in the last video? P-hacking is when scientists mine their data in order to find something that crosses that magical 0.05 threshold of statistical significance, They do this by testing large numbers of hypotheses until one of them dips beneath 0.05. These are almost guaranteed to be false positives, but they are presented as though the researchers found something real. Torturing the data, as it's sometimes called. This problem is often caused by too many researcher degrees of freedom, where the researchers haven't established a rigorous enough methodology before conducting the trial, so they can play loose with the data. Limiting these degrees of freedom can help prevent p-hacking. Another misuse or misinterpretation of p-values in science is to give credence to it without considering what's called prior probability, the probability that is assigned before taking into account the relevant evidence. If scientists don't take this prior into account, they may come to some silly conclusions, such as when this review of the evidence on a homeopathic remedy, which has no possible biological basis for working, by the Cochrane collaboration concluded that further research was warranted. This failure to take into account prior probability can mean we end up wasting time and resources looking into wildly implausible hypotheses. One of the most widely cited papers in the meta-science field was published in 2005 in the PLOS One journal by John Ioannidis, entitled "Why Most Published Research Findings Are False." This is not just a flashy title, it's true. It might sound like a devastating blow to peer review's credibility and reliability, but it's not that simple. Most of what gets published in peer-reviewed scientific journals, in medicine and psychology in particular, are preliminary findings, which have high chances of not panning out upon further research. There are many reasons for this. Sample sizes might be too small to detect an effect. The effect sizes themselves could be very small. There could be p-hacking, too many researcher degrees of freedom, or other statistical blunders and weaknesses that make positive findings more likely than negative ones. There could be conflicts of interest, or even scientific misconduct. Or if a field is young and very popular, early extreme findings are common. This has been termed the Proteus phenomenon. Even when a drug makes it to clinical trials, only 8% of them make it past phase 3. Beyond the high false positive rate of preliminary evidence, it has been noted that much clinical research is also not useful for any real-world application, with a majority of research funds wasted on poorly selected research. As mentioned 2 videos ago, even meta-analyses can be problematic. If meta-analyses are industry-funded, there are significant differences in methodological quality and transparency, and they were, unsurprisingly, more likely to recommend the drug or treatment they were assessing. Perhaps most despairing, a comprehensive review of meta-analyses by Ioannidis found that only 3% are decent and clinically useful, while 20% were flawed beyond repair, 13% were misleading, 17% were decent but not useful, and 27% were redundant and unnecessary. This is in line with the findings that much research funding is wasted on non-clinically useful studies. However, a majority of these meta-analyses were published in Chinese journals, which have been documented to have severe issues. Still, the results are rather alarming, but it does not mean meta-analyses are inherently unreliable or poor quality, just that science is often a slow, messy process. Another quality control problem that spans various fields of science has come to be known as the replication crisis, or reproducibility crisis. Very simply, this is the failure of scientists to replicate the results of scientific studies, either by independent researchers or the initial researchers themselves. Although opinions vary on whether it is indeed a crisis, a survey done by the journal Nature found that a majority of scientists regarded it as a significant crisis, while most of the rest regard it as a slight crisis. Notably, physicists, chemists, and engineers were most confident in the literature in their field. The survey results are very similar to a previous survey conducted by the American Society for Cell Biology. These results aren't necessarily representative of the scientific community as a whole, but they certainly raise some alarm bells. So what's going on here? How bad is the problem? It depends on the field. In medicine, a 2005 study by John Ioannidis surveyed results from almost 50 studies from 1990 to 2003 and found that 44% had been replicated. In psychology, where the so-called crisis is often cited as being the most severe, one estimation puts the successful replication rate at just under 40%, with the subfield of cognitive psychology having the highest replication rate and social psychology having the lowest. An earlier study found that just over 1% of psychology publications could be identified as a replication, as denoted by the term being found in the text and confirmed to be an actual replication. And of these, almost 80% of replication attempts were successful, a much more impressive figure. In psychiatry, one study found that among 83 studies that recommended a purportedly effective intervention, 40 hadn't been replicated, and only 16, or 19%, were successfully replicated. It should be noted that in physics and chemistry, reproducibility issues are much less, since it is much easier to retest initial results. Does all this mean the peer review system is unreliable? Definitely not. As mentioned, much of what gets published in peer-reviewed journals in medicine and psychology are preliminary results, which means they are exploratory by nature and not settled science by any means. It's to be expected that many hypotheses that initially show promising results may later not pan out, especially given the many statistical and methodological flaws we just reviewed and the publish or perish incentives that affect many scientists. For example, it isn't unusual for standard medical practices that are perhaps not based on the strongest evidence to later be replaced by superior practices that are grounded in much better quality evidence. This is merely the process of science sorting itself out over time. Still, one could plausibly argue that successful replication rates are too low, and that's why several initiatives have been undertaken to tackle this exact problem, such as the aptly titled Reproducibility Project for several different fields of science, started by the Center for Open Science and its founder, Brian Nosek. Other fixes to the issue involve more structural changes to science that I'll cover at the end of the video. On the odd occasion, studies that have been published in peer-reviewed journals will later be retracted, often due to serious methodological flaws, but mostly due to academic misconduct, including fraud. The website Retraction Watch provides a window into the scientific community in this regard, documenting retractions as they occur. Although there is evidence that the absolute number of retractions has increased markedly since the turn of the century, the rate of retractions hasn't changed much. It is likely that the growth in retractions is due to the increased awareness of research misconduct and therefore greater vigilance in policing the peer review system. More and more journals are retracting articles, but the frequency of retractions per journal has remained flat. In video 2.3, I discussed the rates of serious scientific misconduct in peer review, usually estimated at about 2%. There is little evidence that misconduct has increased. The final issue I'll cover is one that pollutes the scientific publishing environment. One model for journals to publish that has gotten more popular since the advent of the internet is the open access peer review model. These open access journals mostly publish for free, or when they do charge, fees are generally paid by author sponsors, and the publications are free to read. Unfortunately, this model has been exploited by many predatory open access publishers who will charge publication fees without adequate peer reviewing or quality control. This has ended up with a slew of bogus journals masquerading as legitimate peer-reviewed journals. Librarian Jeffrey Bell used to host a list of many of these suspect journals, which has since been removed in part due to various legal pressures from some of these journals themselves. Luckily, the list can still be found elsewhere online. The problem has been documented several times in various sting operations. For example, a staff writer from the journal Science sent out fake papers to over 300 of these suspect journals and found that over half accepted to publish them for a fee. More recently, a sting operation was conducted that involved sending a fake application for an editor position to 360 journals, some legitimate, some suspect. The application invented a name and made up credentials. About 1/3 of the journals on Bell's list accepted the application. There have been quite a few other stings pulled off to demonstrate this problem. As discussed in a previous video, one way to ensure that a journal is reputable is to look at its impact factor. Predatory journals either do not have impact factors or have fake ones. With all that said, let's put these problems into an overall context. The peer review system has many problems, but it is still an indispensable tool that does work well overall. John Ioannidis summarizes some of the most important fixes that can be made to make more published research true. They are large-scale collaborative research, concerted efforts to replicate findings, this is already being done on various levels, pre-registering studies before they're conducted to combat publication bias, as mentioned, sharing of data, containment of conflicted sponsors and authors, more appropriate statistical methods, standardization of definitions and analyses, more stringent thresholds for claiming discoveries or successes, improvement of study design standards, improvements in peer review, reporting, and dissemination of research, and the reward system in science. However, these problems aren't systemic enough to warrant doubting the peer review system as a whole, which is what science deniers, conspiracy theorists, and pseudoscience promoters regularly do. So, the peer review system is still the best system scientists have developed for facilitating science, yet there are many challenges it continually faces in adapting to an increasingly complex world. The proof that it works is quite simply in all the advancements science continually makes. Perhaps nowhere has this progress benefited our lives more than in the medical sciences. So despite all the shortcomings of the peer review process, it still manages to yield reliable results over time. Before wrapping up this sub-series of videos, I want to focus on one more extremely important aspect of evaluating evidence: intellectual honesty. Join me in the next video for that. See you there!